Good morning, evening, afternoon, or whatever time you happen to be watching this video. I'm Mr. Simonian, and today we're going to be learning about graphing techniques and analysis. And pretty much all of the materials in today's presentation come from something I found from the National Math and Science Initiative, documents on graphs and relationships. I very highly recommend them. Today, we're going to be learning about how to approach graphing problems in AP Physics 1 to find and or calculate important features of a graph like the values, intercepts, slopes, and areas of the graph, and use a table of data to generate a graph and then draw trend lines and use proper graphing techniques to do so. In lots of areas in your life, you're going to run into graphs, whether it's in this class or in another class that you take later or in your daily life. When you're doing a graph, you're basically comparing how quantities in some investigation relate to one another. And if you just look at like a table of data, it's not always apparent how the data are related. Whereas if you plot them on a graph, it can become a lot more clear what, if any, mathematical relationship exists between the quantities that you're looking at. And so being able to read, analyze, and create graphs is going to be a really important skill for lots of different areas, whether you're in like a physics class or another physical science class, whether you do biology or botany or zoology, whether you get involved in something in the social sciences, in business and economics, engineering, health sciences, pretty much any area that you can think of, they're going to find a way to sneak graphs in there. They're really powerful tools for being able to see how things are related. And when we do like labs in this class, we're going to be interested in seeing how quantities that we collect in the lab relate to each other and how changing one quantity might affect another. And so the kind of words that you want to know in terms of the two different quantities that you're dealing with, you're always going to have an independent variable, and the independent variable is the quantity that is being changed or the quantity that you control in an experiment. And when you are creating a graph, you always plot the independent variable on the horizontal or on the x-axis of the graph. Independent variable is the thing that you are changing deliberately, that you are manipulating, or that you are controlling. And as you change this quantity, you see what effect it has on another one. And the one that depends on the independent variable is cleverly enough called the dependent variable. And this is the one that may or may not change as a result of what you do with the independent variable. And you always plot the dependent variable on the y-axis, on the vertical axis. Whenever you are looking at graphs in your daily lives, they can be used to understand different kinds of things about the world around you. For example, this is a graph of world population by country, and it gives us a pretty clear trend that world populations have been increasing, which countries have been seeing the most population increase. And if you're in the social sciences, you'd be very interested in graphs like this for the implications that this has, right? If populations are increasing, there's lots of different things that, for example, a social scientist who's interested in child poverty around the world, they'd be very interested in graphs like this, because if there's an increase in population, generally that is going to correlate with an increase in things like child poverty as well. If you're in business and economics or finance, you might be interested in these kind of graphs because they have implications, for example, with respect to like what kind of stocks and what kinds of companies are going to be more valuable in the future. Well, if population's increasing, then that can give you an idea about like, I would want to be probably investing in companies that are going to be growing as a result of population growth. Some good graphs that to look at are that world population, at least until very recently, had been on the decline for about 2 decades. And you can see which countries have experienced the most world decrease in their percent of their population living in poverty. And these have really important social science implications, as well as just like political implications and things that we as people would probably be interested in, depending on, you know, what fields we end up involved with. And it's quite sad that these trends were looking really good up until COVID. And then according to the World Bank, as a consequence of combinations of COVID as well as climate change, these trends have actually started to go in the reverse. And in 20, they say in 2020, for the first time in the last 20 years, we actually saw increases in the amount of people that were living in poverty. So these are things that we still need to worry about, and that knowing about this information can help you and help us as people in a society figure out, like, how can we try to make these graphs look better, right? How can we make these lines keep going down? So when you're presented with a graph in AP Physics, there's a couple things that you're always going to want to do. And the first thing that you're going to want to do is read the words that are the words of the quantities that are plotted on both axes, both on the vertical axis and on the horizontal axis. It's really important what words are written there, and it can be any of these quantities that you see on your AP Physics formula sheet. Pretty much any of them are fair game to be a quantity that's represented on one of your axes. And once you have found, once you've read the words and found the quantities that you're working with, the next thing that you want to do is look on your equation sheet for an equation that relates both of those axis quantities together. So, like, as an example, you might be given a problem where you're dealing with a force on one axis and time on another, in which case you would want to look for an equation that tells you about force and time. And this approach is really helpful because even if you don't know like how to start or how to approach a problem, going through this process can get you in the right direction, even if you don't really know like how to approach the problem that you're looking at. So always read the words on the graph, find an equation that relates those quantities, and then you'll use this equation to guide your thinking in terms of like what the problem is asking you to do. And so there's a couple things that we need to be comfortable with in terms of finding on a graph. And the first thing is called the value of the graph. And that's just the height of a point on the graph. It's finding both, and really when this is referencing the y value, the height of the graph, like how high you are, would be talking about the y value, but you might also be interested in the x value as well. So like how far to the side the value is on the horizontal axis. And this is an example of a graph that you might see in a physics class. And so this is showing you a graph of force versus time. And the force is plotted in newtons, a unit called newtons, and the time is plotted in seconds. And this is showing you that the value of this, the solid black line is the graph. The value of the graph at t equals 2 seconds, you go up from t equals 2, you hit your graph, and then you go over to the vertical axis to find the height of the graph at t equals 2. And that corresponds to 8. And then the units on this axis are newtons. So one of the things in physics is that the graphs are going to have units on them, and those are things that are going to be important because they affect what the answer is telling you about. You can also do this process in reverse. You could look at the value at t equals you can look at t equals 2 seconds. You could find the value of the graph at t equals 2 is 8 newtons, but you could also say, what about when the force is 10 newtons? From a y value of 10 newtons, you could figure out what the corresponding value of time is by just doing this process backwards. You would look at starting at 10 newtons, you would go over to your graph, and then you would go down to find the time that corresponded to that force. And in this case, the value would be 3 seconds. Another thing that you're going to want to be able to find from a graph is the slope. And when we talk about the slope, that's the steepness of the graph. And the way that you can calculate that slope is by doing the rise over the run. So looking at that same graph, this is an example of a problem where you might be asked to find the slope. The previous example of the value might be a little basic for an AP Physics question, but they might ask you a question about the slope of this graph, in which case you would want to do the rise over the run. And the way that I like to do it is like starting from this point here, I would going from this point here to this point right here. So using the same 2 points in their picture, I would do a rise first, and then I would do the run second. That way I'm kind of going along with the same order that I say the formula, rise over run. So I want to do the rise first and the run second. And when I rise, the value of my rise is based on what's happening along the vertical axis. So if I rise from 6 to 10, that is a rise of 4, and the rise is based on the units on the graph. So it would be a rise of 4 newtons. And similarly, the run, if I'm starting at 1 second and ending up at 3 seconds, that means the run is a run of 2 seconds. So my slope is rise over run, which is 4 newtons divided by 2 seconds. That means my slope is 2, and then the units of that slope are newtons per second. This would be an example of how you might find the slope from a graph. The other thing that you're going to deal with in this class is finding the area of a graph. And when we talk about the area, it's the area enclosed by both the line for the graph, the horizontal or the x-axis, and then 2 vertical lines that are specified by the problem. And because the area is always going to have some starting point, which is the first vertical line, and some ending point, that's the second vertical line, the area is always going to represent a change in whatever quantity the area happens to represent. So kind of going back to our same graph that we've been taking a look at, if they asked you about the area of the graph between times 1 second and 2 seconds, this would be the area that we're talking about. It's enclosed by the graph, which is the solid line, enclosed by the horizontal axis, and then enclosed by vertical lines based on the starting point and the ending point, based on starting at t equals 1 and ending at t equals 2. And if you add up all of these squares, there's 1, 2, 3, 4, 5, 6, and then this right here ends up being 1 square. It's half of these 2 squares right here. So I've got 6 plus 1 gives me an area of 7, and the units of this graph are based on multiplying the units of the vertical axis by the units of the horizontal axis. So the area is 7 newtons times seconds. And in AP Physics 1, you don't need to know calculus. So we will only be finding areas of graphs using either the formula for a rectangle, which is base times height, or a square, which is the same formula, and then also triangles, which is 1/2 base times height. And these 2 equations are on your AP Physics equation sheet. The third thing that you want to be able to find on a graph, sorry, this would actually be the fourth thing that you want to find, is an intercept. And that's the starting value on either the horizontal or the vertical axis. So looking at that graph that we've been considering, this one has a vertical intercept where this corresponds to at time 0, the vertical intercept is 4 newtons. So this force at time 0 starts at 4 newtons, and then from the graph we can see that it increases, the value of the force is increasing as time goes by. And the intercept has the same value as whatever is being plotted on that vertical axis. And if you were looking at an intercept with the horizontal axis, then same deal. The value, the units would be based on the units of the horizontal axis. So just a couple hints about slope and area. If you're dealing with a graph in physics, the quantities on the graph are going to have units, excuse me, and that means that the slope and the area under the graph are going to have units as well. And area is always taken between 2 points. So if a problem ever says from one time to another, or from one place to another, or between one time and one place and another time and another place, that's probably keywords that you need to be finding in area. Whereas if there's only one time or one place being referenced, that's probably asking you about slope, because slope is something that can be found at a single point. Because if you have like a linear graph, for example, the slope at any point on a line is going to be the same. That's what makes it a line. It has a constant slope. So one of the other things that we want to get comfortable with is, given some data like this in a table, we want to be able to come up with a graph, make a graph of that data. And the first thing we want to ask ourselves is, what's the independent variable and what's the dependent variable? Because that tells us what goes on the horizontal and the vertical axis. And a good rule of thumb is that if you're ever dealing with time as one of your quantities, time is pretty much always, it's a very common independent variable, because time, nothing affects, there's no external quantities that I know of that affect time. Time is basically going to go by no matter what. So time's a good independent variable. And if we're given time and speed, then time's going to be what we plot on the horizontal axis. Speed is going to be what we plot on the vertical axis. So I'm going to set up my graph where I draw my horizontal axis. This is where I'm plotting time. And then my vertical axis where I'm going to be plotting the speed. And the next thing that I do after I've drawn my axes is I'm going to label what's on each axis. So I'm plotting speed, and I also write the units, which are meters per second. And on the time, on the horizontal axis, I'm plotting time in units of seconds. Once you've labeled the axes along with the quantity and the units, you want to title your graph. And a good kind of generic title is just saying whatever's plotted on the vertical axis versus whatever's plotted on the horizontal axis. So y versus x is the common title. And in this case, it would be speed is on the vertical axis versus time. What we plot on the vertical axis versus what we plot on the horizontal axis. Once we've got our everything labeled and titled, then we can start using the data to figure out how to scale our graph. So what we want to think about is that our time is starting at 0, and our speed is starting at 0. This is the starting horizontal quantity we're plotting on the horizontal axis. This is the starting value for speed that we're plotting on the vertical axis. And then we want to look at our data and say, okay, our data is going up to 8 seconds, and we want to just use as much space as we can on our graph. So if our time is going all the way up to 8 seconds, I just want to make sure that I'm using as much of my space so I can make my graph as large as I can. And if this is 8 seconds, then I want to probably go halfway, more or less, and that would be 4 seconds. And then in between, halfway again, I would have 2, and then in between, halfway between 4 and 8, I would have 6. And based on this data, I think counting by 2s makes sense, because it goes 2, 4, and then I've got 5, and 5 is going to be halfway in between 4 and 6. So there's where I'll put 5, and then I've plotted, I've shown the values for where all of my time horizontal quantities are going to be, all my time values are going to be, and then I would do a similar thing on the vertical axis. My speed goes all the way up to 20, so up at the very top, I'm going to put 20. Halfway from 0 to 20, we would have 10. From 0 to 10, halfway, we'd have 5. Halfway between 10 and 20, we would have 15. And then we also have this 12.5 data point, which would be halfway in between 10 and 15. So that's our 12.5 data point. So now I have a nice scale for both of my axes. I have quantities labeled, I have a title. Now I'm ready to actually start plotting my points. And just for clarity, I'm going to plot these points in red. The first is at time 0, the speed is 0. So that's this point right here. The next point is that at time 2, my speed is 5. So at time is on the horizontal axis. I go from a time of 2, I go up to a height of 5. That's my next point. The third one is at time 4, the speed is 10. So I go over to 4 and then up to a height of 10. Next is 5 and 12.5. So over to 5, up to 12.5, 6 up to 15, and 8 up to 20. That's what my data look like when I plot them on the graph. And now we can see a really clear, direct relationship or a linear relationship between these two quantities. And once you have your data plotted like this, the next thing that you're going to do is draw a trend line through the data. And your trend line should approximate all of the data as best as possible. It should go through as many data points as possible, with keeping as many remaining points above and below the line. This data is going to be really nice and linear. So what you would also want to do is use a ruler or a straight edge to make sure that you're drawing a nice straight line. That way you have an actual line and not something curved or kind of crooked, which might be what mine looks like. I'm going to try my best. Okay, cool. So as you can see, it's not a perfect, we're not using graph paper right here. And that's another thing, is that usually in class when I'm giving you graphs, you'll have graph paper. So it'll be a lot more precise when we set these up. But we've got a nice linear, all of these points should be on this line if we draw it perfectly. And because this isn't experimental data, this is just kind of getting us to practice this idea of setting up a graph. But once I've got this nice linear graph, now we could do with this graph that we just came up with, we could do all of the things that we were just talking about. We could use this graph to find values, to find intercepts, to find slopes, or to find areas. And now that we've practiced drawing the graph, the next thing that I wanted to practice were those things as well. Just real quick, I'm going to copy this over so we have it for that part of the program. Let's do this. Okay, so just some tips about trend lines. The trend line should be a best fit that approximates all of the data, not just a cluster of data. Use a ruler or some sort of straight edge to draw that trend line. Make it go through as many points as possible with equal points above and below the line. And when we're using graph paper, the best practice and getting data in a lab, it's best practice to not use the data points to find the slope, but to use points on your trend line to find the slope. For these examples, it's good enough. And I think on the AP physics test, in fact, if you use points on the line, they won't take off for it. But it is a best practice to not do that and to only use points that end up on the trend line, not the data itself. So let's just real quickly talk about what we did when we set up that graph. We basically went through this procedure. We identified the independent and the dependent variables as the first thing. That helps us know what we plot on the horizontal axis, that's the independent variable, and the vertical axis, that's the dependent variable. And when you are in a science class, time and math as well, actually, time is a common independent variable because no external quantities affect time. Next, you pick a scale that is going to make sense in terms of your graph, and it's going to include all of your data and make the graph as large as possible. As we go through, you'll build intuition for number 3, which is deciding if an origin makes sense for your data. In our example, 0 was a data point, 0, 0, the origin was a data point already. But later on, we'll build intuition for based on the quantities we're working with, does it make sense to have an origin value or does it not? Then you plot your data just like we did. You include all of your data points and you darken them, where you're plotting again, independent variable on the x-axis, dependent variable on the y-axis. Once you've got your data plotted, you draw a trend line if the data is linear, and if the data is not linear, then you draw a smooth curve that fits the data as best as possible. And it might be tempting, but never connect the dots when you're drawing graphs in physics. Title your graph. That standard title that you can always use is quantity on the vertical axis versus quantity on the horizontal axis, and then label those quantities as well as their units on the respective axes. Once you do that, you've got an awesome graph just like the one that we made. So here were the 2 questions that I wanted us to answer based on this graph that we just came up with. The first thing that I want us to come up with is the slope of this blue trend line. And so remember that our slope is rise over run. It's the rise of the graph divided by the run. And so what I'm going to do is I'm going to draw the rise in green, and I'm going to pick 2 points that are on the line. So I'm going to pick this point right here and this point right here. Notice that the rise is this. That's my rise. Starting at a height of 15, going up to a height of 20. So the rise is 5, and the units are based on the units of the graph, which are meters per second. And then I'm going to do my run in orange. That's my run. Show it right here. And notice that my run is starting at 6 seconds and going over to 8 seconds. So the run is 2 and the units are seconds. So my slope is rise over run, which is going to be equal to the rise, which is 5 meters per second, divided by the run, which was 2 seconds. So 5 meters per second divided by 2 seconds. That's my slope. 5 over 2. And from there, I do division. 5 divided by 2 is 2.5, and then my units come out to meters per second divided by seconds. So we could say meters per second. The slope is equal to 5 divided by 2 is 2.5, and the units are meters per second per second. Once we start unit 1, we'll learn about what this quantity is representing. This is an important physical quantity that we've just figured out by just looking at the slope of the graph. So that's something that's just really interesting about physics, is that the slope of graphs actually has a lot of significance. It has units, and it also is going to represent a new physical quantity that we're going to be learning about. That was part A. Part B was asking about the area of the graph from t equals 4 seconds to t equals 8 seconds. So notice it's from t equals 4 to t equals 8. When you have the area of a graph, it's always the area between the graph, which is the blue line, the horizontal axis, which is the time axis, and then two vertical lines specified by a starting point and an ending point. And we're starting at 4 seconds. So I'm going to draw a vertical line at 4 seconds to enclose the horizontal axis in the graph. And I'm going to do the same thing at 8 seconds, going up. And now I've enclosed this area, and this is the area that they are asking about. So we can shade that in, at least in a light way. That right there is the area that we are being asked about. And notice that this area, if we break it up into two pieces, if I draw a horizontal line right here, that this area is a rectangle plus a triangle. So that's what we're going to do for part B. We're going to break that area that they're asking us about into a rectangle and a triangle. The area is going to work out to be the area of a rectangle plus the area of a triangle. And on your formula sheet, you have the formula for both of those things. The area of a rectangle is base times height, and a triangle is 1/2 base times height. And then you would look at these geometric figures and figure out, put in this would be probably my base, this would be my height, really, because it doesn't matter which one you assign, as long as you're consistent and call one the base and one the height, you'll always get the right answer. So for my rectangle, I'm going to say the base goes from 4 to 8. And when you write these values, you include the units as well. My base is this length along the time axis, starting from 4 seconds, going up to 8 seconds. So my base is 4 seconds, times my height starts at a height of 0, goes up to a height of 10, and it's on the speed axis, which has units of meters per second. So the height then is 10 meters per second. And then I've got plus, then I've got plus 1/2 the base, which is the base of the triangle, which is this distance right here, going from 4 to 8. So in this case, the base of the triangle is the same as the base of the rectangle, also 4 seconds. But the height is going to be different. We're starting, actually the height's going to be the same too, because we're starting at 10 and we're going up to 20. So the height, again, is a height of 20, and on the vertical axis that has units of meters per second. So notice when we're multiplying these quantities together, we've got seconds times meters per second. And if we've got seconds in the numerator and in the denominator, then these seconds are going to cancel. The seconds here cancel. Same thing here when I multiply 4 seconds times 20 meters per second. The seconds on top cancel the seconds on the bottom. So overall, these numbers have units of meters. So this area that I found represents some distance or some quantity describing a distance with units of meters. And that's going to be 4 times 10 meters, which is 4 times 10 is 40 meters, plus 1/2 of 4 times 20. So 4 times 20 is 2, 4, 6, that would be 80, and then 1/2 of 80 is another 40. meters. So it looks like that area works out to 40 meters plus 40 meters, which is 80 meters. That is the area that they asked about. And again, the area has physical significance as well. It's representing, in this case, it's representing how far the object traveled as it was moving over that time. From 4 seconds to 8 seconds, over that 4-second time period, it traveled 80 meters. As we get through this class, we're going to get very comfortable dealing with these kinds of things, dealing with the fact that our graphs have units, that our quantities that we're working with have units. So don't let the units intimidate you. We're going to get practice with this as we go through. As long as we're comfortable drawing these graphs, looking at the graphs, interpreting things like slopes, calculating areas using our geometric formulas, then we're going to be in good shape. And as always, if y'all have questions or need help, have come and see me during intervention or during another time that suits your needs. So I had already mentioned these hints about trend lines, and that was the last thing I needed to mention. So thank you guys so much for your time, for your patience, for your participation. Have a good one. Make sure you turn in the focus notes for this assignment, and I will see you guys in class where we are going to do a lab over using these graphing techniques. Take care, and I'll see you next time.